Good afternoon. For today's lesson, we're going to look a little more into um, distributions when we have continuous numbers for our data. If you recall, in the previous section, we did make a distinction between continuous numbers and discrete numbers. With solid, sort of countable discrete numbers, to calculate probability, we used many times the binomial distribution formula if it was appropriate for that situation. With continuous numbers, we have a bit more of a challenge. We need to know how those numbers are distributed along the number line. Meaning we need to make a picture of it on a curve and take a look at what type of distribution it forms. And we looked at a couple of different types. We looked at uniform distributions, and we looked at triangular distributions and that type of thing. We're going to focus in this section on normal distribution, which is a very often occurring distribution of data. So first of all, just to review a little bit about the normal distribution, this isn't a new concept to us. We've actually looked at normal distributions, what they look like. Here's an example of a curve, and here's some other normally distributed data sets. Normal curves take on many appearances and many different means and standard deviations. A couple things I want to point out in all of these. Here we can see our mean, which is signified by the sigma symbol there, is 64.4, so somewhere between 64 and 65. Notice that that's located at the center of the curve. And in fact, that's always true for all of these sets. We see that mean determines where the curve is centered. Here it's 3, here's at 9. And then when we look at the standard deviation, it determines how wide and how high our curve is. The bigger the standard deviation, the more spread out our data value is around the mean. And the smaller the standard deviation, the higher the curve, because more of the data is gathered around the center. So if you'll notice that all of those different curves we can put to something we call the standard normal curve. Every one of these curves has a different formula that would describe it, and each of these curves has different areas between points because they're all different shapes. And as you know, different shapes, just take triangles for examples. When triangles take on different shapes, their areas change. So to make it a little easier and to translate this, we create what's called a standard normal curve. And the standard normal curve never changes. It always has the same parameters all the time. The standard normal curve is always symmetric and bell-shaped like all the other curves. The mean is 0 for the standard normal curve, and the standard deviation for simplicity is always 1 and -1. And then, of course, with all normal curves, the total area under the curve is equal to 1. And we call the x-axis a horizontal asymptote, as theoretically this curve continues to go out in each direction for infinity, never quite reaches the x-axis. So we call that x-axis an asymptote. So how do we translate the data we have on our curve over to the standard normal curve? The way we do that is with this little formula. It's called the z-score formula. This number here is called my z-score, excuse me. And of course, this x here represents an individual data value. We'll see how that relates in a second. We subtract the mean, we divide by the standard deviation, and that gives us what we call a z-score. What this does is it translates any given value for our individual data set and tells us what it would be on this standardized curve called the standard normal curve. So literally you can think of this formula as a translation. It's translating what it would be over on this curve from whatever data set we're given over here. So here's an example. if we know data has a normal distribution and the mean of that data is 48 and the standard deviation is 5, and we wanted to convert this to what it would be on the standard normal curve, we could do that. You can see that if I spread out, we get a standard deviation of 5. So here I'm adding 5 as I go to the right, adding, subtracting it as I go to the left. We can see that 45 right here would be somewhere between 43 and 48. As we plug 45, which was our individual data value we're concerned about, and we subtract 48 from it, and divide that difference by 5, we get negative 3/5. That translates into negative 0.6. Negative 0.6, though it's off the screen here, is what this value would be. And you can see that makes sense. Negative 0.6 is smaller than 1, and so it doesn't quite get all the way over to negative 1. So you can see in a general sense here that they're in the same relative place on the curve. This 0.6, because on my standard normal curve, standard deviation is 1 and negative 1, can be interpreted as being how many standard deviations our individual data value, in this case 45, is from the mean. So I know that my data value is not that extreme. It's not even 1 standard deviation from the mean. It's kind of in this basic area where a lot of my data values are gathered. Now, the z-score can be helpful to us in identifying how unusual or how not unusual an individual data value might be. The most important thing that we use the z-curve for in the standard normal curve is to find percentages and areas under the curve. It's indicating a percentage of a population that will fall within a given range. So for example, here I may be curious to know what percent of my data falls between A and B. Now instead of using the equation that describes this particular data set and trying to use calculus to determine the area between A and B, we could translate them into what they are under the standard normal curve, and from that information we would be able to calculate the area under the curve. And we're going to see how to do that here in a minute. Now the one way we can do it is by using the z-table. In fact, this is how most of our areas used to be found, is using the z-table. We've got to replace that with technology, which we're going to look at here after we examine the z-table. But there is a z-table that I posted in the WAMAP that you can refer to, or you can always Google one. There's a million of them out there. They're all the same. So for example, if we were wanting to know what the area would be to the left of the z value equal to 1.75, we can kind of, actually we're calculating for negative 1.75. If we look that up on the z-table, the way the z-table works, we look at down the side here to find the first two numbers, negative 1.7, and then for the 5 in the hundredth spot, we go across the top and we find the column that has 5 in the hundredth spot. And the intersection of those two tells me what the area is to its left. The z-table will only give us area to the left of a given z-value that you look up along the side. So we can see here that to the left of negative 1.75, we only have about 4% of my data. That would be the area to the left of this value. Now if we took positive 1.75, since there was about 4% to the left of negative 1.75, then the area to the left of positive 1.75 would be 1.9 or 0.96, so 96%. So in other words, 4% to the left of negative 1.75. We can assume on the other side that the area to the right of positive 1.75 would also be about 4%. So the area to the left would be its complement, 0.96. All right, if we look up 1.23 on the z table, you can look it up right now. You would see that the area to its left, when we look it up on the table, is 0.8907. Also looking at your table, how would we find the area to the right of positive 1.75? Well, we can take our answer up here and simply take its complement. The area to the left, or to the right, of positive 1.75 will be the complement of whatever the area is to the left of 0.96. So that would leave me with about 0.04. And then what about to the right of positive 1.23, excuse me? Well, again, that would be the complement here of 0.8907. One of the easy tricks you can use in finding the complement is to look at your numbers and add them up to 9. So in other words, I have an 8 here, so I know it's going to be 0.1, and then I already have a 9, so it's going to be a 0, and then 9, and then the last digit should add up to 10, so it'd be a 3. So we have 0.1093, just a nice little trick you can use to pull you away from your calculators. All right, now that we've kind of looked at the z table, let's look a little closer at how we can use technology to find it, because that's pretty much what we're going to be doing in your homework. Unfortunately, the z table is sometimes not specific enough for us, so we turn to technology as an alternative to that. So on your calculators, the function for finding areas under the normal curve is found by going to second vars, and vars is a button right underneath your arrow keys there, and above it says distribution, D-I-S-T-R. And so basically we're going to the distribution menu because we're hitting second first, and then choice number 2, normal CDF, is the way we're going to be looking at areas, cumulative areas. We won't be using the PDF ever. Now, when you pull it up, the 4 pieces you need to enter, 4 pieces of information, all of your screens might be slightly different, are these 4 things. First of all, we need a lower boundary, and second of all, an upper boundary, third, the mean, and fourth, the standard deviation. When we talk about the lower boundary and the upper boundary, this is kind of the tricky part, and I'm going to illustrate that here on the next slide. So, say for example, we're after the area to the left of 1.45, and again, we're on the standard normal curve here for our first illustrations. So on the standard normal curve, 1.45 is going to be a little bit less than halfway between 1 and 2. Now you'll notice that we're going to the left of 1.45. Well, the one problem that we have is that because the horizontal axis is a asymptote, this curve continues to go on and on and on for negative infinity, down through negative infinity. Well, there is no negative infinity button on your calculator. So there's no real lower boundary, but we still have to put one into our calculators. And so the way we do that is we just pick something that's extreme enough on the left that it would be considered infinity. So you just need to pick a really big negative number, and then if you're on the right, you want to pick a really big positive number. For example, if we were going from 1.5 to the right. So in this case, one of the numbers, I just pick negative 1,000. If you remember, once we get to negative 3 and positive 3, going to the empirical rule, we've captured about 99.7% of our data. That only leaves 0.3% of our data. So anywhere beyond negative 3 is going to be a tiny, tiny area. And so if we go to negative 1,000, it's just as good as going to negative infinity. So what you can see, and if you visualize this with me, And this is one of the reasons why it's really important to draw a picture when you're entering these into your calculator of how your data is laid out and what you're after. Is we're kind of trying to create a left-hand and right-hand box limits to what we're putting into our calculator. And so you can kind of picture it like trying to box in the area that we're after. So in here, my lower boundary, because it's on the left, is negative 1,000, comma, there's a comma button on your calculator. Some of you may need to put that, some of you may not, because it gives you a list to put it in. But if you just get normal CDF with an open parenthesis on your screen, way to go, second bars, choice number 2, this is exactly how you want to enter it, negative 1,000 all the way up to 1.45. This is my right-hand boundary. And then when we're dealing with z, the mean is always 0 and the standard deviation is always 1. When you hit enter after entering that information, you should see 0.9265, which represents the area between, and so hence the area between these boundaries that we have set up here. This would represent a 92% of my population, 92.65%. All right, another example, here we're going to the right. I'm being given a value that's on the left, 2.153. Now, if you'll notice, here's a z-score that went out to 3 decimal places, which we're not able to do with tables. And in many of the problems that you're dealing with in WAMAP, if you try to use the tables, you may end up sometimes having your answer rejected. And that's only because they're just trying to get you to be a little more specific. If we were using the tables, we would simply have to just round this up, or round this off to 2.15, which is going to give us just a slightly different area. The negative 2.153 is a value that's to the left of 0 because it's negative. You'll notice all the numbers over here are negative. And we want to know its area to the right. And so now it's the upper side, the upper boundary, that is unbounded. So we have to pick a number to put in there. So we're going to use 1,000 positive. And so notice now negative 1.53, negative 2.153 is on the left. It's my left-hand boundary. 1,000 is my right-hand boundary. Whenever your infinite boundary is on the left, it's going to be negative 1,000. If it's on the upper boundary, it's going to be positive. Comma 0, comma 1. And we find that the area between these is about 98.4%. All right, what if we're going between two values? So here, I don't have anything that's unbounded. In fact, we're looking for a very specific area between two definite boundaries. And so infinity doesn't come into play here. We're just going from negative 2.153 all the way up to positive 1.45. And we find that area to be about 0.9108, or about 91% of my data. All right, so here we're going to, here's another example, sorry. Find the area between the z values. See if you can find that on your calculators. And you can pause the video at this point, find it, and then you can confirm if you found the right values. All right, so now that we found that, how could we look at that in terms of probability? Well, the curve itself, remember, is representing all of my data values. And so it is, in probability terms, my sample space. The shaded area, which would be the area that we're after, is going to represent the successful outcomes. So that would be like my event space. So the way we could phrase this is, what's the probability a randomly selected value would have a z outcome that's between negative 2.18 and positive 1.44? We'd say it's 0.9105. So we can look at this curve not only in terms of just percentages, but we can look at it in terms of probability as well, as we were doing in the last section. All right, so let's find the probability a random score would fall as follows. And you're going to use your calculators to find this. I want you to find the probability that if we were to select a random z-value, that it would be a z-value less than 1.43. Pause the video. The outcome is 0.9236. Here's the next one. What's the probability a given z-value would be greater than negative 0.81? The answer for this one is 0.7910, or 79% probability. The probability that z would be less than 2.81, than negative 2.81, and less than at the same time, negative 1.14. Here we have two boundaries to our values, and we see that only represents a percentage of my data of about 12.46%, or 0.1246. So the probability that a random z-value would fall between these two numbers is about 12.46%. Remember that your probability p should always be a number between 0 and 1. If you get a probability that's outside of that, there's probably something wrong in the way that you've entered the data. Since the standard normal curve is the way we standardize all populations that are approximately normally distributed, to connect the two, we use that z-score as a bridge, a translation from our set of data to the standardized curve. Now, there are four basic probability problems. Probability that something is less than some value, as we looked at. Probability it's greater than some value. The probability that it's between two values, and last but not least, the probability it's less than one value or greater than another value. So let's look at some examples here with actual data. Example 1, we have body temperatures that are normally distributed with a mean temperature of 98.6 and a standard deviation of 0.73. So what's the probability that if we select a random person, that person would have a normal body temperature that's less than 96.9 degrees Fahrenheit? So here I do want you to see the translation going from one data set to the other. Here's how our actual data is set up, where the mean here is 98.6. We put it at the center. And 96.9 is a value that's less than 98.6, right? Just in terms of numerical value, it's to the left somewhere. We don't know exactly where. But I can figure out where exactly by finding its z-score. So we subtract the 2, divide by 0.73. I want you to note that if you're typing this into your calculator, you have to put parentheses around this top subtraction to keep the order of operations working the way you want it to. And what we find is it's negative 2.33. So one of the ways that we could find the probability of having a body temperature less than 96.9 is to, on the z-table, or even using our calculators, to find the area to the left of negative 2.33. So we could go negative 1,000 all the way up to negative 2.33, right? Lower boundary all the way up to this upper boundary, 0, 1, and we find it's 0.0099. Now, the other way that's a lot easier for us, again with our technology, is to actually use our data values. So use this curve. Because in the technology, we can actually plug in the mean amount and plug in the standard deviation amount of the actual data, and it will give us the same area that we would have gotten had we used and translated them into z values. This is where the calculator becomes much more easier to use to calculate these areas. So we would say that the probability that a randomly selected person would have a body temperature less than 96.9 is 0.99%, or slightly less than 1%. So now, in these problems, you'll notice a lot of them I've tied to the normal curve. And as we move through not only this section, but the next section, and then also going into problems dealing with uh, the central limit theorem, these are all involving the z-curve. So it's really important that you practice drawing a picture and getting used to what these numbers mean in terms of that picture. Because otherwise they just become numbers you're plugging into your calculator, and they can get really confusing. So here's another situation. The replacement times for CD players are normally distributed with the mean of 7.1 years with a standard deviation of 1.4 years. Find the probability that if we select a random CD player, it will have a replacement time of less than 8 years. So go ahead and see if you can actually plot this data into your calculator correctly and get the answer to that. I'm going to pull up that pause at this point. Okay, so as you're putting it in, you should have something normal CDF negative 1,000 all the way up to 8, comma 0, not comma 0, but comma 7.1, which is the mean, and then comma 1.4, which is your standard deviation, and you should get 0.7398. This is how you would write it in probability notation. So also practice writing that out in probability notation as well. Getting used to the inequality symbols will be really key for you going forward. All right, go ahead and find the probability that a randomly selected CD player will have a replacement time of more than 9 years. All right, so we would write that as probability that x is greater than 9. And here we can see that the probability is about 8.74%. How about a replacement time between 5 and 8 years? So here we have two definite boundaries. On the lower end 5, on the upper end 8. X is less than 8. And reading this backwards, x is greater than 5. We see that it accounts for about 0.6730 the timer, 67.3% probability. And here's an interesting one. This is different. We'll have a replacement time that's less than 5.1, or, remember, or signals addition, greater than 9.1. All right, in this one, we actually have to put the word or in between them, right, as two separate things, because it's either less than this or greater than that. So basically, we're looking for two tail regions. Now, putting that into your calculator can be tricky, because really you would have to do two calculations that you add together, right, going to the left of 5.1 and then adding that to whatever's greater than 9.1. But one quick and easy way to do this is to find the area between 5.1 and 9.1. So find the area in between and then subtract that from 1. So go 1 minus and then do normal CDF with the two boundaries being 5.1 and 9.1. If you subtract them, what you are left with, if you find this complement, is what's left over in the tails, 0.1531. All right, so for our last example here, we're going to just use another set of data. Scores on a midterm exam are normally distributed with the mean of 73 and a standard deviation of 9 points. What is the probability if we chose a student at random has a score between 80 and 90? Calculate that on your using your calculator. And actually, I'm going to put all of these up there. Pause it and then come back. What you'll find is the first one, probability x is between. Notice I'm using x now. X is the symbol of my data as opposed to when we have them written as z-scores, I use the z symbol. But x is a universal symbol we use for data itself. between 80 and 90, it's about 18.89%. For the second one, it comes out to be about 0.0073. At most 85 would translate into less than or equal to 85. And I want to point out here, this is an important concept, that whether I choose less than or equal to, it actually does not change the probability in a continuous data scenario. That's because the probability that a randomly chosen score would actually equal 85 in a continuous scale that would be exactly 85, no decimals, blah, blah, blah. The probability of any one score is near zero. So putting the equals there or not having it there does not make a difference in your probability at all. And here we have, again, less than 55, greater than 91. So here you'd want to go 1 minus normal CDF, the area between the two, and you should get, this should actually be the word or, not the word and. And that concludes this lesson on finding the z-score.